So these are notes as much as you want. These are relatively straightforward concepts. I'm not expecting any large degree of difficulty here. Before I forget, I need to get those tests back. So, work, kinetic energy, and potential energy. This is sort of an introduction. A lot of this will be sort of stuff that I already covered yesterday or Friday. Okay, so the nature of work. In the everyday sense, work involves pushing, pulling, lifting. There has to be a force involved, right? Has to be a force involved. And work is the amount of energy that is transferred when a certain force acts through a certain distance to do some job. So key words there, energy must be transferred. There has to be a force, and there has to be a distance. There must be movement. And I should point out, the force and the distance must be in the same direction, or at least components, right? If I lift something, and I went through this, I think if I'm holding the box full of Hot Wheels cars here, and I move it over to here, have I done any work? And the answer is no, because I haven't really applied. I've applied a little bit of force to get it moving, but then once I get moving, I'm moving at a constant speed. The force is all up. The force is up. The distance is sideways. No work done. Okay? And the other idea is that I haven't transferred any energy. So energy is transferred when work is done. So that's sort of the key idea. When the question is, has work been done? You ask yourself, has there been a transfer of energy? And if the answer is yes, then there's work. If the answer is no, then the answer is no work. Okay, so transfer of energy in a horizontal sense. Horizontal force is applied to a dynamics cart for a certain distance. Work is done, i.e. energy is transferred to the cart. The cart now has kinetic energy. If I push something, right, pushing it across the table, I give it a push, it has kinetic energy. Right? Now, back to grade 11, the box slows down. How come? I pushed it, I stopped pushing, objects in motion to stay in motion, but how come it stops? Friction. So I apply some work, I transfer energy, it becomes kinetic energy, and then the kinetic energy of the box is removed, it slows down. Where does that energy go? Heat. Right? Friction slows it down in its heat. Now obviously that didn't burn me, but if you rubbed it on there enough, then that would, like, that's the whole idea about like rubbing two sticks together, right? Rubbing your hands together. That friction is an increase. When you do this, you're applying force, you're doing work to move your hands back and forth. Friction is there, slowing them down. Your energy is transferred into heat. Okay? But in this case here, the cart now has kinetic energy. Work and energy are sort of equivalent, and they are measured in the same units. Note that when a force is applied at an angle, cart moves horizontally. The only force which does useful work on the cart is FAX. Right? So the X component is the force that is doing the work. What about the FAY? What's it doing? In this case, what's it doing? Lifting it up, and it's in fact reducing friction, right? But only in this case, FAX is doing the work. And you guys already know that FAX is FA cos theta, right? All kind of covered on Friday as well. I'm sort of just doing it in note form. And I'm going to give you some sample problems today. Okay, what about vertical transfer of energy? Here's a guy lifting a box. I don't know why I said bricks. It's coated on bricks. When objects are lifted, work is done. A certain force is exerted through a certain distance, right? You apply a force upward, and the bricks, the box, whatever it is lifted through a certain distance. Energy is used up or transferred to get the job done. As you lift something, you are transferring energy to the box. And then that energy is stored as what kind of energy? What's it called? Starts with a P. Potential energy. But the kinetic energy of the bricks is zero. They are at rest. Where did the energy go? we say that it has transformed into what is known as potential energy, which is stored, air quotes, inside the bricks. Is there like a place to store this energy in there? No. Can you see the energy with special energy goggles? No. It's really just a description. If you go way back to like that first week of grade 11, it's a model, it's an explanation, it's a way to describe something that we can't see. We talk about this energy. All good? I'll be posting these, so if you want them, you can put them up. Energy, potential energy is energy that is stored in an object because of its condition or its position. Okay? So we would say the boulder, the rock right here has a certain amount of potential energy, and that energy is relative to, depends. If you're talking about down there, base level, it has a certain amount of potential energy. If you're talking about to that level there, it has a certain amount of potential energy. Same idea as if the deck of cards is here on the table, here on the second floor. It's got a certain amount of potential energy relative to the floor. It's also got a certain amount of potential energy relative to the ground floor, right? We're all 25 feet in the air here, right? You don't stop and think about that too often. But we all have potential energy just because we're on the second floor. If you were to fall down the stairs, you would have a lot of kinetic energy at the bottom. I don't recommend that. Okay, what about springs? When we stretch out or push in a spring, we do work on it. We transfer energy to it. We say this work goes toward increasing the potential energy of the spring. When you stretch it out, it has potential energy because when you let go, it's going to bounce back, right? And if you push it in, then it has some potential energy because it's going to bounce back. And some springs are designed to be like at rest. They just sort of sit there and you can't really compress them, but you can stretch them. Some springs are designed to sit there like this and they're designed to be pushed, and some are designed to sort of go back and forth, right? And would you say that some springs are stronger than others? Yes, that's true. Now there is a lab coming up, which I think I'm going to wait till I get back. I'm going to do it out of order. By the way, that reminds me, when you guys are ready for working springs, I pre-taught the lesson yesterday. I sat here by myself, taught the lesson, and yes, it was weird. So Mrs. McDougall's going to play that for you probably Thursday. Okay? Hopefully that goes well for you. Or if you want, I guess you can all sit and watch it individually. Up to you. You guys can decide. In general, anytime work is done, energy is transferred to an object and increases its kinetic or potential energy. There, if I had to sum up what you need to know about work, it's that. Anytime work is done, energy is transferred to an object and increases its kinetic or potential energy. When your solar-powered battery, your solar-powered calculator, right, it absorbs energy from the sun, from the lights, and it stores it in a capacitor as electrical potential energy, right? Solar cells will store that energy as well. When you plug in your phone to charge, you're taking energy from the electrical grid and you're storing it inside your phone as electrical energy. Work is done. Okay, so what is this magical formula for calculating work done? Well, it's probably the easiest formula you've ever seen so far. By the way, this unit is actually fairly easy compared to the last couple ones. So it's a nice sort of home stretch unit. Okay? Keep that in mind. This is one that it's easily achievable to get like high marks. So take advantage of it. Because I set you up, now you're going to get a low mark, Martin? If you don't do anything, then what? Well, that's true. You do have to do some work. Don't slack off. I'm just saying here's an opportunity where you can, do really well. So, work is proportional to the applied force. Work is proportional to the distance moved. Work is not related to time. Whether you do a job fast or slow makes no difference. Now, that's not true sort of in real life. People want the job done in a certain amount of time. That's called deadlines. That's important. it still takes the same amount of energy because it's the same job. Okay, so we are working our way towards a formula, and I'm just going to give it to you because it's so simple. Work is proportional to FD, and I told you a while back to turn a proportionality into an equation. You simply insert, what's this K thing called? Yeah, it's called the constant of proportionality. Yes, my handwriting's bad. Okay, where F is measured in newtons and D is measured in meters. So, what is this magical K value? Well, we've just defined, we as in the science community, have defined the basic unit for work is the Newton meter. And that is referred to as a joule, capital J, named after this guy over here, Charles? I can't remember his first name. One joule is defined to be the amount of work done when a force of 1 Newton acts through a distance of 1 meter. So a 1 Newton is like hardly anything at all, right? Like 1 Newton is the amount of force required to hold an apple is what they always come up with because it's a Newton thing. I would say a deck of cards would be about the same. So I'm providing about a Newton here of force, and so if I lift it through a meter, that would be 1 joule of work that I just did, right? How many card lifts do I have to do to burn off a whole breakfast? A lot. You'll be surprised. You'll be shocked, actually, when we actually run the stairs and you find out your personal power rating, how much stair climbing you have to do to burn off a bowl of cereal. You'll be shocked. So 1 joule is the amount of work done when a force of 1 Newton acts through a distance of 1 meter, and that's called a Newton meter, which we've defined to be 1 joule. Because we define it to be 1, it conveniently eliminates the K in the equation, because this is Newton meters, and a joule is equal to 1 Newton meter. Okay, because this is a defined thing, because we've made up this concept of work, it's not like circumference and pi and diameter, where there is a number that makes the circle work. It's not like that kind of thing. It's not like UCM where it was 4 pi squared. We've defined it to be 1. If we wanted, we could have said that 1 joule is equal to be 100 Newton meters, but then we'd have to have a K value of 100. Well, that would just be a lot of extra, pardon the expression, work. So we don't do that. That's it. Shall we do some sample questions? All right, so you have these sample questions. These are like incredibly simple problems. Work done against friction. How much work is done when sliding a 30 kilogram chair a distance of 15 meters across a rough surface where the force of friction is 50 newtons? So in other words, you've got an applied force this way, and you've got a friction force this way, and the friction force is 50. It doesn't say that it's a constant velocity, but it doesn't say acceleration, so you're going to have to assume that those two are equivalent, right? So the friction force is minus 50, the applied force is 50. All you're going to do is you're going to go work equals FD. Why can't I make F's today? $50 times 15. 50 times 10 is 500. 50 times 5 is 250. 750 joules. Note that what? It is positive, that's true. Is work a vector quantity? No. Well, I'm not actually real sure, but having said that, force is, right? D is just a distance, it's not displacement, but force is a vector, so I do believe that work is a vector, so there can be positive or negative work. That's right, Connor. Negative work would be like when you take energy away from. right? Like friction would be slowing an object down, something like that. But what I wanted to point out was that the 30 kilograms doesn't come into play. Okay, because that 30 kilograms is kind of built into this friction force of 50, right? If I didn't give you that, if I gave you a coefficient of friction, you'd have to find the weight force and the coefficient and the normal force, and then you could get friction, and you could do it that way. Okay? All good? Okay, what about work done against gravity? Vertical work. How much work is done in lifting 2 bricks, each a mass 1.4 kilos, from the floor to the top of your table at a distance of 80 centimeters? Are the alarm and bells ringing that centimeters should be converted to meters? I hope so, although I will say that many of you made that mistake on that last test. What's one thing you can do on a test? Always check units to see if it's centimeters or grams or any of those things. Know the basics. I don't like doing that trick to you, but I know that if you go on and take post-secondary science, they're going to pull that stunt on you almost every time. I'm trying to train you in a relatively safe environment. Okay, notice also that they pull these kind of stunts. There's 2 bricks. So what is the total mass here? 2.8. Okay, so we are lifting here, right? So we've got a weight force, and we've got an applied force, which is up. The first step would be to find said weight force, mass times gravity. So 2.8 times 9.8. Now, I guess technically that is negative, and therefore the applied force is positive 27.44, right? And you're lifting it up. So the work done is FD. So that force is really the applied force, 24.44 times 0.8. And again, I'm without calculator. 27.44?
You got the first one.
It's 21.952.
No. Up one? Okay. Why you got 24?
Change that beta.
Oh, I did, didn't I? This should not be 24. This should be 27. How did I mess that up?
We don't know.
Now, what would I do on a test like that? If you got everything all nice and organized, no, I'd give you the full mark.
Wrong. It's wrong.
Give you the full mark. However, if it's on a multiple choice,
Wrong.
it's kind of hard for me to see that, right? So those are the kind of things you got to be careful of when you're doing multiple choice. And yeah, my first year physics, every exam, 100% multiple choice. Every single question. Yes. Well, you got a 25% chance of guessing. That's the one good thing. 75% chance of guessing wrong. Okay, what's this work up to? 21, I heard you say, Bailey?
21.952.
Say 21.95, and that would be joules. These kind of questions could easily be multiple choice because they're relatively straightforward. And I'm hoping you won't mess them up. This time we have it being pulled at an angle. How much work is done on the cart? Do you guys have a picture?
No.
Okay. 1.5 is our mass. Our angle is 30 degrees. And the FA is 25. And the cart moves a distance of 4 meters. So what do you have to do? Job 1 is to find the horizontal component, FAX. So that's going to be 25 cos 30. 21.7. And now it's a simple matter of going, work equals FD. What is the force? 21.7. The distance is, whoops, 4. Are you kind of hoping that they get a little bit harder than this? This is a good level, Connor? 86.8 joules. Relatively straightforward. I would also caution you into not doing too many of these simple questions, right? Like if you just keep doing these, you're not going to get any better, right? I mean, do a few, yeah, okay, I get it. Look for hard ones, move on, right? There's going to be harder ones coming. Is there one more? Oh yes, inclined plane situation. So we got to go back to, here's a great review of unit number 2. How much work is done to pull the cart up the plane? How much work is done in lifting the cart straight up? And how much work is done if there is a friction force of 15 newtons up the plane? So this is sort of the hardest one here. Make myself some remember. Oh yeah, so how much work to pull the cart up the plane? So it's 6 meters up the ramp. Do you guys have the picture? Okay. How much FA do I need? I need enough FA to overcome the FD. And you might remember, I hope you do, that FD is mg sine theta. $30 times 9.8 times the sine of, it looks like it's 30 degrees. The heck, where's my... I've never seen that on a calculator. 147? It's really weird. Usually the sine and cosine tan are right beside each other on the calculator, but this one, the sine is here, the tan is there, and the cos is up there. It's very weird. Must be made in some place that... Okay, so 147 newtons of force, so how much work? F equals FD, 147 times 6, 882 newtons, or not newtons, 882 joules. That's part A. Part B asks for how much work is done lifting the cart straight up. What if you have the cart right here and you simply lifted it? Well, the force required would be the weight force. It's a large one. It's 30 kilograms times 9.8. $294. But you only have to lift it? How far? 3 meters. So the work is F times D. 294 times 3. Do you know what it's going to be? I hope you do. What is it? It's 882. Why is it the same? Should it be the same? Martin says yes. Why yes, Martin? We get it to the same spot, exactly. What are you going to say, Connor? No? You were going to say the same thing? Well, how much potential energy does it have there? 882 joules. Does it care how it got there? No. Doesn't care. It just knows that it has 882 joules of work. Now, why do we use ramps? Notice that the force required here is only 147. Here the force is 294. It's easier to push it up the ramp. Right? But the trade-off is it's easier, but you have to push it farther to get the same amount of work. Okay, now, how much work is done if there's a friction force of 50 newtons up the plane? Because there's always friction at play, right? If there's 50 newtons up the plane, that means that my applied force for C is going to be my FD plus my friction force. I'm going to need 147 plus 50. Why am I using a calculator for that? 197. And am I going to end up with more work? Yeah, because you got more force. FD, right? I'm using 197 newtons of force. The D is 6. 1182 joules. Well, now, I just finished saying that the amount of potential energy there is 882 no matter how you got there. But if there's friction, how can we have more potential energy?
There's something slowing us down.
Yeah, that's kind of it. Do you have more than 882 joules of potential energy? No. What happens to the other, whatever it is? Heat. Energy is lost in heat. How much?
That, subtract.
You could subtract the 2, or you could just take the 50 times 6, which would be 300 joules of it. 300 joules is heat. Now, it's still easier to push. It's still only 197 joules. You still got to push it farther. Yeah, you generate a little bit of heat, but the force required is less. Does that make sense?